Here's a special function which I call the juggling function. Given a point on the x-axis, move it up to the function, and then move that point back down to the x-axis along the tangent. We have the special property that no matter where we start, applying this 3 times always gets us back to the initial point. Now, each update here is actually Newton's method, which is usually used to find the roots of a function. In this case, our function has no roots, and by the way it's constructed, every point is trapped in a 3 cycle. We can see this by drawing all 3 points at the same time and seeing that they just map to each other. Moreover, we can actually write down the equation of this function explicitly by solving a particular differential equation. And what I want to do today is take you through that derivation, so you can do this for yourself. Let's start by recalling Newton's method. Given a function, in this case x squared minus 2, we want to find a root. We're going to start with an initial guess, x0 equals 2, and define an update rule, which gets us the next point, which should be closer to the true root. The way this works is by moving up to the function and moving down along the tangent, and we get a simple equation which tells us how to find the next point. Notice that after only 3 points, we're already within 4 decimal places of our proper root. Now let's see how this works in general. So to get to the juggling function, I want to take you through a series of questions that will hopefully remind you about Newton's method and lead you to how we could discover this function ourselves. Feel free to get some pen and paper and do these questions yourself. Learning maths is best achieved through actually practicing. So you can pause the video now, and then I'll go through the solutions as we go. So remember that to write the equation of a line, it's given by y minus y0 equals mx minus x0, where m is the slope of the line, and x0, y0 is a specific point which lives on the line. In this case, our specific point will be xk, then f of xk for the y coordinate, and our slope will be the derivative at xk. And so the equation of our tangent will be y minus f of xk equals the derivative times x minus xk. If xk plus 1 is the intercept, which is the next point obtained by Newton's method, this is given by substituting in x equals xk plus 1 and y equals 0. Substituting that in, we obtain this formula where xk plus 1 is being written purely in terms of xk. And rearranging, we obtain our update rule. Take the previous point and subtract the derivative and the function where the function is being divided by the derivative. The question is whether this always works. We saw that it worked for x squared minus 2, but does it work in general? The answer is, of course, no. One reason being that, well, a function might not have any roots, for example, x squared plus 1. Of course, Newton's method will never find a root because there are no roots to be found. But even for functions that have a root, a simple example being y equals log of x, a bad initial guess will lead us astray. In this case, if we guess an initial point too far to the right, the tangent line goes through the negative values. And so the next application of Newton's method will give us an error because we're trying to plug a negative number into the log function. What we want to do is even worse. We want to find a function where, no matter which guess we start with, we always get led astray. To do this, we're going to rig Newton's method using another function r. What we want is that every time we update our guess for the root using Newton's method, this update is being decided by the function we already chose. So we start with the function r. We're going to find the function f, whose Newton's method update rule is given by the function r, and then we're going to do this in a special case. Again, feel free to try before I go through the solution. So from before, we had that our update rule is given by the following formula. And what we want is that this is obtained by substituting xk into r. Now, for notation purposes, I'm going to set x equals xk and y equals f of xk. And we notice that we get a differential equation. Rx is equal to x minus y over y prime. Rearranging this, we get y prime over y equals x minus r of x. And integrating on both sides with respect to x, we get 1 over y dy is equal to the integral of 1 over x minus rx dx. On the left side, this is the logarithm of y. And so to undo this, we need to take an exponential. So our solution will be that y equals e to the power of 1 over the integral x minus rx dx. I could have had a plus c here, but because I only want a specific solution, I'm going to assume that c equals 0. So here is our rigged function whose Newton's method update rule is always r of x. What about in a particular case? If r of x equals minus x, then no matter which point we start with, when we apply Newton's method, we should get the negative of that point. Let's find the function that does this. What we need is that y equals e to the integral of 1 over x minus r of x, which is minus x. And so we'll end up with 1 over 2x dx. And this is e to the half, the logarithm of the absolute value of 2x. A half in the exponential power can become a square root, and then the e and the log cancel out. And so this function is simply the square root of the absolute value of 2x. Let's see this in practice. Here's the graph of our function. We're going to take the initial point 2, move it up, and move it down along the tangent, which goes to minus 2, and then minus 2 goes back to 2. And we see that this point gets trapped in a 2 cycle. And in fact, no matter where we start, Newton's method always overshoots the true value of the root and takes every point to its negative value. What about order 3? This is how we obtain the juggling function. We're going to start with our rigged function, r of x, which is 1 minus 1 over x. First, show that no matter which point we substitute into this function, applying it 3 times always gets back our initial value, and then solving the integral from the previous question to find f in this case. Once again, feel free to try yourself. So when we plug x into r of x, we get 1 minus 1 over x. And doing that twice, we get 1 minus 1 over 1 minus 1 over x. And to do it 3 times, we need to put in r again. So this is the full expression for subbing x into r 3 times. To simplify this fraction, I'm going to multiply the top and bottom of this fraction by x to give 1 over 1 minus 1 over x minus 1. And then we're going to multiply the top and bottom of this fraction by x minus 1. Now, luckily, some cancellations happen. X cancels with minus x to get minus 1. And we end up with 1 plus x minus 1. These cancel out, and we just get x. So for example, taking the value 2 and plugging it into our function gives a half. Plugging in a half gives minus 1. And plugging in minus 1 leads back to 2. And this will happen for any point at all that we substitute into our function. What about finding f, the function whose Newton's method update rule is r of x? As we saw before, we have to solve an integral. And we get e to the 1 over x minus r of x, which in this case is 1 over 1 minus x. We're subtracting, so there's a double negative. And we can multiply top and bottom by x. Now this is a linear over a quadratic, so we're expecting to see a log somewhere. We want the top to be the derivative of the bottom, which is 2x minus 1. And so we're going to multiply by a half out the front to get a 2x, and then add in a minus 1 to ensure we have the derivative of the bottom. Now to make up for that, we need to add on the bit that we subtracted. And because we're adding inside the exponential, we can turn that into a multiplication. In the first term, we will get log of x squared minus x plus 1. Because of the half, we can do the same trick as before, and this ends up being a square root. And for the second term, we have a square down the bottom, which we can turn into a perfect square by completing the square to get x minus 1 all squared plus 3 over 4. And so this becomes the arctangent. So what we get is e to the power of a half, 1 over root 3 times arctan. And figuring this out, and once we divide by the appropriate term, we end up with 2x minus 1 divided by root 3. So let's see this in practice. Here is our juggling function from the introduction. We take the point 2, apply Newton's method to get a half, again to get minus 1, and then again takes us back to 2. Each time we apply Newton's method, we're actually just applying our rigged function r, and that's why we get a 3 cycle. Putting all 3 points together, we have the property that we want. Thanks for watching, and I hope you enjoyed.